It's your turn. Consider the data in the table below. The reaction here is 2A plus B plus 3C will yield 3D plus E. Now you're given a set of experiments 1 through 4 and sets of concentrations of the reactants A, B, and C along with the rate of E forming in moles per liter times seconds. Now what I'd like you to do is to pause the podcast, write this data down, and then when you go on to the next slide, it will tell you what you need to do with this data. Welcome back. From the data you've already written down, these are three things we can find. We want you to determine the rate order for each of the reactants and write the overall rate equation for the reaction. Then I want you to determine the overall order of the reaction, and then finally calculate K for the reaction, ensuring that your units are correct. Be patient as we work through the solution. You hopefully already have numbers that will match mine. This is your time to check yourself. These are going to be extended out over a number of slides. So again, you do need to be patient. Pause the podcast when you need to look at what I did compared to what you did. For the first, I'm going to find the rate order for A. And in order to do that, I want to use experiments 1 and 2, because between experiments 1 and 2, the concentration of A doubles, but the concentrations of B and C stay the same. So as long as B and C are staying the same, I don't have to worry about those. And here I'm taking the ratio of my concentrations raised to some power x is going to be equal to the ratio of my rates. The ratio of my concentrations is 2 raised to some power x is equal to the ratio of my rates, which is 2. So 2 raised to some power x is equal to 2, so x must be equal to 1. So this reaction is first order with respect to reactant A. For the rate order for B, I'm going to use experiments 2 and 3. And the reason I'm going to use experiments 2 and 3 is that the concentrations of A stay the same, the concentrations of C stay the same, only B changes, and that's what will make this easiest to deal with. So I take again the ratio of my concentrations of B, 0.4 moles per liter over 0.2 moles per liter raised to some power x are equal to the ratio of the rates, which are 0.080 moles per liter times seconds divided by 0.020 moles per liter times seconds. I have the ratio of my concentrations as 2 raised to some power x are equal to the ratio of my rates, which is 4. So 2 raised to some power x is equal to 4. X is equal to 2. So this reaction is second order with respect to reactant B. We are left to calculate the rate order for C. We're going to use experiments 2 and 4 here. And the reason we're going to use experiments 2 and 4 in order to calculate C is that the concentrations of A and the concentrations of B are consistent, the same in both experiments 2 and 4, whereas the concentration of C doubles from 0.2 to 0.4 moles per liter. So I take my ratio, 0.4 moles per liter divided by 0.2 moles per liter, raised to some power x equal to the ratio of the rates, and in this case the rates are the same between both experiments. So I have 2 raised to some power x is equal to 1, x is equal to 0. So this reaction is zero order with respect to reactant C. We now have the solutions to parts A and B. Our rate equation is based on the rate orders that we just determined. So our rate is equal to K times the concentration of A. Because it's raised to the first power, I do not need to show the exponent there, and then times the concentration of B squared because it is second order. Now the overall reaction order is the sum of the exponents. So the exponents here would be 1 for A, 2 for B, so the overall reaction order is 3. We don't have to show the reactant C because it's zero order. That does not have to be shown in the equation because a change in the concentration of C does not affect the rate. Hope you've done well so far. Here we're going to go ahead and show you the solution to part C, which is a determination of K. I rearrange the rate equation so that I isolate K by by putting rate on top of a ratio divided by the product of the concentration of A times the concentration of B squared. So on top I'll have my 0.010 moles per liter times seconds divided by 0.20 moles per liter and also divided by 0.20 moles per liter squared. Here's where I need to make sure I cancel my units correctly, and when I do that, my units will end up being liter squared on top over mole squared times a second, and after all the multiplication and division of numbers, I get 1.25 liters squared per mole squared times a second. Let's try another problem. Here we have a radioactive decay process. These are first order in terms of reaction kinetics. So we have a solution prepared at a strength of 1 mole per liter of iodine 128, and it's 0.15 moles per liter in strength 68.5 minutes after mixing. What is the half-life of the radioactive isotope I-128? Let's see how you did. This is how I would solve it. I would first write a data table. I hope your data table looks like mine. We know that the initial concentration of the I-128 is 1 mole per liter. The concentration at time, in this case 68.5 minutes, is 0.15 moles per liter. Our time again is 68.5 minutes. I need to find the half-life, but in order to find the half-life from looking at my equations, I know that I need to find K first. So I'm going to try and solve for K, and I'm going to use an integrated rate equation in order to do that. I hope your solution looks like this. If it did not, you may want to pause the podcast now, go back and rework it before you come back and look at my solution. Here's the solution for K. I've isolated K. It's equal to the ratio of, on top I have the natural log of the ratio of the initial concentration of I-128 over the final concentration of I-128 divided by time. So I go ahead and put my numbers in. It's the natural log of 1 mole per liter over 0.15 mole per liter divided by the time of 68.5 minutes. Now the natural log of that ratio of concentrations is 1.897. I divide that by 68.5 minutes, and that gives me a K value of 0.0277 per minute, or minutes to the -1. Now, one thing that you have probably noticed is that all K values for first order reactions have the units minutes or seconds or hours, some time unit to the -1, or the inverse of that time. Now we can go ahead and solve for T1 half. Again, this is a lovely equation to use because it's very simple. T1 half is equal to 0.693 divided by our K value. So 0.693 divided by 0.0277 per minute gives us a half-life of I-128 of 25 minutes. We've come to the end of part 4 of the video podcast series on kinetics here at Ontario High School. I want to leave you with this quote: "A wise man is superior to any insults which can be put upon him, and the best reply to unseemly behavior is patience and moderation."